Thank you very much, Tiffany, for the kind invitation and also the very generous introduction. So I am a person who works on the mathematical foundations of machine learning. And when it comes to that, people usually think about probability and statistics um, as a founding pillar. But I'd rather say that there are other areas of mathematics that are also very useful. For example, dynamical systems, differential equations, geometry, and computational math. And and moreover, it really should be a synergy of all those mathematical tools that interact with machine learning in a feedback loop that can enable interesting applications. So this talk will try to provide some examples. It'll have three parts. The first part will be on the optimization of functions defined on a manifold. And if you are an expert, I will actually be speaking of a situation where there is actually momentum. So I'll be actually considering accelerated optimization. And then I'll take the tool developed in part one to sort of consider a stochastic generalization where I will be actually sampling a statistical distribution defined on manifolds. And in particular, the focus will be on a special class of manifolds known as Lie groups. And finally, the preparations in part one and part two will enable me to do something called generative modeling of data on Lie groups. And this is really the end goal of the talk. So let me first say a few words about why you should care. So here are some applications. So on the left is really just a molecule, the configuration of a molecule. But this molecule is actually generated. So this is actually taken, this beautiful picture is taken from this great work, this Nature paper, which now is actually a Nobel Prize winning work, where they actually use diffusion models to generate the configurations of proteins so that people can do things like drug discovery, etc. But if you want to describe the configuration of a molecule, at least the common approach is actually to use angles, and angles are actually living on Lie groups. So this is why you want to do generative modeling on Lie group. What is on the right, on the other hand, is a newer application. It's actually an area that we initiated and we are trying to push. So there we are actually trying to mimic the success of the design of molecules, where now we want to design quantum processes. For example, you may actually want to design quantum circuits that perform certain functionality, and we actually do that in a generative modeling setup as well. It's a generative modeling on Lie group setup as well because quantum processes are actually living in unitary groups. So there you still have to actually do a lot of things to respect the geometry, and then you can get better performance and more trustworthy result. Okay, so I will actually elaborate all those applications later on, but let me start being more concrete. So part one, accelerated Riemannian optimization. So it'll be primarily based on two papers. The top one is joined with my student Lin Kai Kong, Yuqing Wang. It's a more recent paper in iClear 23, but also I'll be combining the presentation with some results from this older paper with Tomoki Osawa that was from AI Stats 2020. It won the Best Paper Award. So so the context in part one will be on optimization of a function on a manifold, and I will start the presentation with a special case of Stiefel manifold. So what is a Stiefel manifold? A Stiefel manifold is so sorry, so this admit thing is blocking my view. Um, so a Stiefel manifold is actually a very concrete object. So you are considering n by m matrices. And you are basically requiring the matrix to be orthogonal. More precisely, so you are dealing with not necessarily square matrices. So it's n by m, but you are requiring each column to be orthogonal to all the other columns, which corresponds to this quadratic constraint. There is a special case, so that's the actual orthogonal matrices case. So if you are actually dealing with square matrices, so n is equal to m, then then the manifold actually has an additional group structure, and you actually have something called an orthogonal group, which is a Lie group. In general, however, you don't have a group structure. And why do I want to optimize a function defined on a Stiefel manifold? So here are some examples. So let me start really with a motivating toy example, which is nevertheless quite important. So here I'm considering the problem of given a matrix, n by n square matrix, how do you compute its largest m eigenvalues? And there are a lot of applications in which n is huge, like a million, but you only care about, say, the top 10 eigenvalues. So m can be very small. And in this case, you actually have a lot of issues. So if you, for example, use some traditional approach, you can't even store this matrix in its entirety. So you have to do something else. Here is one approach. So you can actually cast the problem as an optimization problem, where you basically maximize over this X matrix, which is n by m, and it has to live in the Stiefel manifold. The idea is you let this X basically encode the orthonormal basis of an m-dimensional subspace of this n-dimensional space. So it's a very low-dimensional subspace of a very high-dimension space. And then you basically project this A matrix to this subspace. If you take the trace of the projected result, you are really summing over the eigenvalues. So you're basically looking for the subspace, the best subspace to project to, such that the sum of the eigenvalues of the projection is actually maximized. So if you do that, you will basically locate the eigenspaces, the eigenspace of the top m eigenvalues. And that's why you can actually leverage Stiefel optimization to do this task. But it's very important that you actually need to do this in an exact fashion. So in machine learning, especially when it comes to practitioners, people have the trend of thinking, oh, I can implement any constraint. I just have to add a regularizer to the loss function. So you can add a regularizer to this loss function to enforce the near approximation, the near satisfaction of the constraint, but that's not good. Because you will actually destroy the orthonormality of the basis, and then your result will actually be very wrong. So here you actually have to do this optimization exactly on the manifold. Uh, of course, you may say, oh, that's, sorry. So you may say that's an easy problem. This is just a quadratic objective function. So how hard could it be? Well, so first of all, it's actually very hard because this is not even a convex optimization problem because you have a constraint, and the constraint itself is non-convex either. And for example, you have complications like there is no unique minimizer. I mean, if you shuffle the basis, of course, you get the same result, etc. So this is already a pretty hard optimization problem. But if you are still not happy, here is a harder problem. So this is a practical application called projection robust Wasserstein distance. So it's basically an application where you can compute the distance between two probability measures. So there are many ways to compute the distance between probability measures. For example, Wasserstein distance is a very useful one. So given mu and nu, you can basically consider in something called a Cantor-Rovich problem. Basically, the idea is, okay, so you have two piles of sand, one corresponding to the shape of mu, the other corresponding to the shape of nu. You basically want to move the pile of sand in the shape of mu to form the shape of nu. And if you do that, of course, usually you want to minimize your efforts. You want to minimize the motion of sand. Uh, so you can actually formulate an optimization problem and show that um, the optimization problem can really be cast in this fashion where you basically have to minimize over a joint probability distribution pi whose margin x marginal is mu and whose y marginal is nu, and then you try to sort of minimize the distance of travel. Of course, the actual theory is much more complicated than this. It'll take a whole lecture to describe. So let's just accept that this is a very useful thing to compute. but it's computationally very costly to compute, especially in high dimension. So so um, so actually, as a collection of leading researchers had proposed this idea of projection robust Wasserstein distance as a remedy. So the idea is, okay, so because this Wasserstein distance is very hard to compute in high dimension, why don't we actually consider a low dimensional surrogate? So in many cases, your data actually have some low dimensional structure. So if you are lucky, and your data actually has a low dimensional subspace structure. So suppose most of your data points are actually concentrated near a subspace, and then you can basically look for this subspace. So like before, we can encode subspace using an element in the Stiefel manifold. And then you can prove that, okay, so if you consider the projection of mu and nu to the subspace, and then the computation of the Wasserstein distance is basically what I have circled here. So you can just compute this quantity in order to get the distance between the projected distributions. And then, of course, you still have to do this outer maximization over the subspaces, but overall, this is computationally more manageable if the subspace dimension is much lower than the ambient dimension. Moreover, it has been argued in a very compelling way that this is robust. For example, so suppose you have an outlier. So suppose most of your data actually live in a low dimensional subspace, but you have some outlier. And then after doing this projection, you basically get rid of the outlier. So there are many reasons why this is a very cool object. But in terms of the optimization problem per se, you see, okay, so you still have to optimize over Stiefel manifold, and you have to do it exactly. It's a bi-level optimization problem. So the function you're really trying to optimize over the Stiefel manifold is the solution to this inner minimization problem. So it's a rather complicated function. So so you can actually have very non-trivial situations in which you want to do this optimization. The final example is new. At least it's invented by us. So the paper was 2023. So in machine learning timescale, this is not new anymore. But still, this is newly invented by us. So it's a way to improve transformer. It's a generic improvement. In a nutshell, transformer is a very powerful deep learning architecture, and it was first invented for natural language processing, where you deal with sequences, but now it's sort of revolutionized this computer vision as well. So let's just think about sequence. So it's based on attention mechanism, which has an infinite reference window, which is good for dealing with sequences. For example, recurrent neural network has a short reference window. And of course, therefore, a lot of efforts have been made. For example, GRU and LSTM have longer reference window, but attention mechanism the transformer really has infinite reference window, and it's implemented by something called an attention layer. So you have this multi-headed attention mechanism, um, which sort of characterizes the correlations between tokens in your sentence, in your prompt. Uh, and they can characterize long-range interactions, and that's why you have a long reference window, roughly speaking. And how do you get those correlations? So you don't actually get that a priori, so you actually learn that from your training data. So each attention head actually has trainable parameters, which are those weight matrices. Um, and very roughly speaking, the weight matrices actually correspond to ways in which words actually interact with each other. And notably, there is no unique way in which words interact. There can be multiple correlations. And these are actually, again, learned. But then we ask ourselves, okay, so suppose there are multiple ways in which words are correlated. Um, are they really orthogonal to each other? If they are not, can we actually make the correlations orthogonal so that we don't really keep on wasting our attention very similar correlations? So mathematically, this just corresponds to making these weight matrices to be on the Stiefel manifold. So we actually tried our idea So sorry, let me slow down. So then the training problem becomes, okay, so previously you sort of optimize over those W matrices, which are really just in Euclidean spaces, but now we do the training by optimizing our model over Stiefel manifolds on which these W's live. So we tried this idea on vision transformer. So we took the vanilla vision transformer and we just added this orthogonality constraint, and then we actually got results that are much better, way much better than the Euclidean version. Um, of course, vision transformer is a very important idea. So there are a lot of later fancier models. So there are a lot of fancier models that can actually be outperformed by our idea. So we don't have to do anything fancy. We just change 2 lines of code, change the optimizer from Euclidean to Stiefel, and then we can get results much better than a lot of the improvements of vanilla of Vision Transformer. But of course, there is a caveat. So actually, there are two. So number one. It's not like Stiefel optimization will automatically buy you advantage. So if we train it by our optimizers, we get improved performance, but there are existing manifold optimizers. Some of them may actually give you results that are worse than Euclidean situation. The other caveat, which is related, is that we don't have a proof. The transformer loss landscape is extremely complicated. It's highly non-convex. We actually have proofs of convergence in non-convex situations as well, but that's really just like the tail behavior. So eventually you sort of land in some convex neighborhood, and then you can have convergence. You can even have rates, but still that's not enough. That's not enough for you to understand how you actually get into the local well. So even in the Euclidean situation, I think this is something that people don't know how to do. We don't know how to do that either in our situation. So really, we only have empirical observation of interesting behavior and actually pleasant results. But I'd love to hear if people have ideas about why that is the situation. Um, but anyway, so hopefully I motivated enough why we care about optimization on Stiefel manifold uh, or manifold in general. The question is, how do we do it? So mathematically, we will actually adopt a variational approach, which is actually going to be very friendly to non-Euclidean spaces, and also it naturally introduces momentum. And momentum is really the same thing as what we have learned in mechanics. So you cannot really avoid talking about mechanics without mentioning Newton. So Newton said, okay, so the rate of change of momentum is given by the force if you have a conservative system. So if you take the objective function as the potential, and then this Newton's law can be written as simple differential equations. Q is the position of your particle. Q changes according to momentum. Momentum changes according to the conservative forcing. And then Lagrange came along. Lagrange said, "Oh, that's great, and it's actually, the what you see on the surface of something deeper." So Lagrange said, okay, you can consider a variational principle. So you define an action function of S. It's a function of Q. Q is a function of time. So if you define this action to be the integral of something called a Lagrangian, which in this case is basically kinetic energy minus potential energy, and then you consider the critical point of this infinite dimensional action functional, and then you get the critical point satisfies basically an infinite dimensional equation that's actually going to be exactly this Newton's equation. So this is called the Euler-Lagrange equation of this variational principle. In this case, it's exactly Newton's equation. You may wonder, how is this relevant to optimization? So far, there's no relevance. I did intentionally take this F to be the potential, but at this moment, you should be puzzled because this is a conservative system. The total energy is actually going to be a constant. So if you run this dynamics, all you will see is constant exchange between the kinetic energy and this potential energy. So F will not be minimized. But if you think about it, that's really because your system has a time translational invariance. So more precisely, If you do a time shift of q, you get the same action functional. So you actually get conservation of total energy by Noether's theorem. But that shows us a path. So actually, in a beautiful paper of Andre Wibisono, H.R. Wilson, and Michael Jordan, they sort of broke the time translational symmetry of this variational principle by adding an artificially created time discount to this Lagrangian. And then if you write down the corresponding Euler-Lagrange equation, you get a simple second order ODE, which has this additional term. And if you prefer, you can rewrite it as a first order system. And then you see, okay, so the forcing now is no longer just this conservative forcing, but there is an additional frictional forcing, which removes energy from the system. So you can actually, take that idea and prove very easily that because of this additional term, the position actually converges to a local minimizer of f for sure as time goes to infinity. Again, you may think this is very trivial, but it's actually creating profound connections to existing optimization theory. So, for example, so when gamma is equal to 2/3, and by the way, you can choose gamma because you can choose r. So you can choose r such that gamma is 2/3, and then one discretization of this optimization dynamics actually corresponds to the celebrated method of Nesterov accelerated gradient for convex function. So this is actually a beautiful paper by Weijie Su, uh, Boyd, and also Candace. So it's actually landmark work. And also, if you choose gamma to be a constant, then some discretization of this continuous dynamics gives you Nesterov accelerated gradient for strongly convex function, and another discretization gives you a Polyak heavy ball. And all these should be contrasted with gradient descent, which is actually an Euler discretization of gradient flow dynamics, which has no momentum. And momentum makes a difference. For example, so the C in NAGC stands for convex F. So if F is convex, you can prove that NAGC converges like 1/k squared. And in some sense, this rate cannot be improved. But gradient descent only converges like 1/k. So this is one of the many reasons why people say if you have momentum, then you can get accelerated optimization. So all these are classical results, and what I'm trying to do is to generalize this momentum acceleration to Riemannian manifold. And if you think about it, this is actually non-trivial. So the approach that we will take is not going to be based on the differential equation. It's actually going to be based on this variational principle. So let me first say a few words about this differential equation and why it's not easy to start with. So okay, so if you look at this differential equation, it uses the gradient to create a dynamics that does the optimization. So what is gradient in the Riemannian situation? So here is a non-example. So consider just the 2x2 orthogonal matrices and a toy loss function, which is the determinant of that matrix. A careless person would say, oh, then great, you have everything because you just compute the determinant, you collect all the partial derivatives, and that's your gradient. That's wrong. So in fact, for orthogonal matrices, the determinant is always going to be either +1 or -1, and on each connected branch, it's the same constant. You have the one single sign. So you feel like the gradient should really be 0. So what is the contradiction? The reason is because even though this is a 2x2 matrix, because of the orthogonality constraint, you really have a one-dimensional manifold. The dimension is not 4. A, B, C, Ds are actually related to each other. You cannot really collect partial derivatives as if things are independent. So of course, that's just the tip of the iceberg. So manifold optimization is a profound field, especially in the momentumless situation. So the contribution that we have here, roughly speaking, are a new way, an intrinsic way of introducing momentum and an improved speed, convergence speed, and also consequently better accuracy. So like I said, so we do so by using variational principle. So variational principle for Euclidean optimization is something that I already talked about. So you use basically this artificially created Lagrangian. So you may say, oh, then great, that's easy. So if you have a manifold situation where instead of having a trajectory q as a function of time, you have a trajectory g, which is a function of time, it's really just like so I intentionally used a different symbol just to emphasize that I have a curved situation. So this g corresponds to particle moving on the manifold. You want it to move to the local minimizer of your loss function. And you may say, oh, that's easy. I mean, you compute g dot, that's going to be living in the tangent space. All you need is a Riemannian metric so that you can define a notion of kinetic energy. So in theory, you can do that. You can even write down the Euler-Lagrange equation corresponding to the critical point of this variational principle. If you are really good, that will correspond to optimization dynamics. In practice, the equation, the ODE that you will get is going to be not explicit at all. And if you want to discretize it in order to get an actual algorithm, that's going to be a nightmare. So a lot of people tried in a different context, not in the context of optimization, but in the context of doing dynamics on Lie group. Uh, this is so far not really solved. So that's why we will actually adopt a different approach. So in this paper joint with Tomoki Ozawa, we had a solution if G, this manifold actually has an additional group structure. So in that case, you have a Lie group and you can do cool things. So the technique we will be using is called trivialization. What is the idea? Okay, so you know that G dot lives in the tangent space. The tangent space is a very nasty object to deal with because as G moves, the tangent space will change. So you have to do things like parallel transport, etc., so that you can sort of maintain your tangent vector in the tangent space. And comparing tangent vectors, everything is a mess. Um, so we do this. So instead of considering G dot as the momentum, which really should be called velocity, but I'm happy to tell you more about the difference offline. So instead of using G dot as a momentum, you sort of pull everything back to a fixed space, which is a tangent space at the identity element of the Lie group. That's called the Lie algebra. So this is called a reduced momentum. This Kc variable is the momentum that we will be using, and you can define very easily a notion of kinetic energy. So unless people care about it, I will not say too much about it, but you can do that. And then your momentum really lives in a Euclidean space. So this is a flat space which is not changing. And this makes all the differences. So you can actually write down the corresponding ODE. Again, it takes some effort, but by the end of the day, you get something like this. Okay, so position changes according to something. What is this something? It's no longer just the momentum, it's G times the momentum. So you really should think this Kc as like an angular velocity, and G is like length. So if you multiply length by angular velocity, you get velocity. And then this angular velocity changes according to something like a net torque. So this I actually maps the angular velocity to angular momentum, but again, don't worry about it too much. So you have a net torque. The last term is again the conservative forcing. The first term is a dissipation. That drains energy from the system. The second term is nu. It's a Coriolis force term that accounts for the curved geometry of the manifold. So this is the optimization dynamics that we have. So you can prove very easily it converges to a local minimizer, but this is not an algorithm. So far, this is a mathematician's toy. So we have to have an optimization algorithm, and we can do that by discretizing the time. So there is something that I will not have much time to talk about, but basically you can pick the geometry. I mean, you design the dynamics, you design everything. Everything is up to you to design. So you can pick some geometry so that you can actually cue this Coriolis force term. So that's not too important. Um, so that's not too important. But then the question is, how do we discretize the time of these dynamics? So we use an operator splitting scheme. So we write the vector field as the sum of two vector fields. This one with g dot equals 0, and this one as with c dot equals 0. The great thing about the first dynamics is that even though this forcing term is as nonlinear as you want, G is a constant, so this forcing is actually going to be a constant. So you can write down the analytical solution to this equation. It'll be basically given by this solution to the linear SDE. Similarly, the second equation is linear because it's going to be a constant. So you can write down the analytical solution to this equation, to this dynamics, and then you basically do h time evolution of the first dynamics, h time evolution of the second dynamics, and then you iterate. So this is called operator splitting scheme. So by this iteration, we go from k to k plus 1 first in C, and then from uh, k in G and k plus 1 to G at k plus 1, so we can iterate. So this is going to be a first order Lie group optimizer. So if you care about order actually doesn't matter too much. So for experts, here we are using something called a Trotter splitting. If I can use a high order splitting scheme, and I can make the method arbitrarily high order. So high order is easy. What is not easy is acceleration. So you remember the goal of introducing momentum is to actually show that to get some accelerated optimization. But this problem is actually solved in a recent paper by my student Lin Kai and me. I will not talk about it too much. What I do want to talk about is number one, you exactly preserve the group structure. So your optimize that your optimization actually stays exactly on the manifold. You don't have to do any projection. It's just automatically preserving the group structure. Uh, for the sake of time, let me not say too much, but rather just say, okay, that's because you're solving equations analytically, and all those equations actually keep you on the manifold. Also, the method is explicit. This is very important. So there are a lot of existing approaches that do numerical integration of dynamics on Lie group, not necessarily in an optimization context, but more general. But those methods typically are implicit. You have to solve a system of nonlinear equations, which is going to be a nightmare if you're dealing with high-dimensional machine learning applications. We don't have to deal with that. Our method is completely explicit. So everything's good, except I really swept a lot of things under the rug. So I talked about optimization on Lie group. I didn't really say too much about optimization on Stiefel manifold. They are technically not the same thing. They have some intersection, but that's it. But still, that's not enough. So if you do Stiefel optimizer, you can leverage the same mechanism, but just more advanced techniques. So you can use more advanced variational principle, more delicate discretization to do it. For the sake of time, I will not say too much about this. But let me first summarize the part one. So by using a variational principle on manifold, we can start doing optimization. You have to do a trick. Well, you don't have to, but we use the trick, which is this trivialization, which allows us to get momentum variable, which is Euclidean. And this is going to be really, really good because then we can actually do optimization pretending everything is on a flat space, but the dynamics and the optimizer actually secretly keeps everything on the manifold. That's of course because we actually have structure preserving integrators. But as a consequence, we will get accurate and efficient gradient descent method with momentum on Lie group. Okay, so that finishes part one. So let me now start talking about a stochastic generalization, which is part two. So this is a joint work with the same student, Lin Kai Kong. COT is a top conference in learning theory, so it's a very good conference. So the task that we will be considering is called sampling. So just to fix the terminology, let's first review what is sampling in Euclidean space. So you are given a probability density function, usually unnormalized, and you want to generate samples of random variables that follow this density. So this is a problem that is so important that there are so many methods. A good amount of them are actually centered around something called overdamped Langevin dynamics. The idea is, okay, so if you define the potential to be negative log of the density, or normalize the density, and then you consider overdamped Langevin dynamics, which is gradient flow plus an additional noise term, Then under mild condition, your solution will actually converge to this Gibbs distribution, which is exactly your target distribution. And now I want to do the same thing on manifold. Why do I want to sample on manifold? So there are a lot of applications. For example, so if you care about physical sciences, a lot of people do uh, statistical mechanics of molecules. And very often molecules are described by reaction coordinates such as bond angles. So if you have an angle of 2 pi, it's the same as 0. So you are actually not going to be dealing with things in the configuration in the Euclidean space. You are actually having the configuration in a manifold. And if you want to do statistical mechanics, very typically you want to sample from some distribution of the configuration. So that's why you want to do sampling on manifold. If you care about data sciences more, for example, so there is something called Bayesian neural network where you don't really make each weight parameter as a constant, but you treat it as a random variable. And then if you do what I did in part one, putting some geometric constraints on some of the weight matrices, then you have to be sampling from this manifold, sampling from some manifold in order to do inference of Bayesian neural network. If you don't care about data sciences or physical sciences, how about a combination? So if you do data assimilation, for example, you want to predict the weather or the climate on our globe, then you often want to do things in a Bayesian approach. So you want to basically sample from some posterior distribution, which accounts for your prior knowledge as well as your observations of the weather. And then you will be sampling from the sphere. Again, that's a manifold. So this problem of sampling from manifold is so important that there are actually a lot of existing approaches. So roughly speaking, you need Brownian motion on manifold, which is very difficult to implement. So that's why people have been actually discretizing Brownian motion so that you can actually have some implementable method. And then maybe I should have said that Brownian motion is easy to define on a Euclidean space, but on a manifold, it's very difficult to implement exactly. So that's why you have to make approximations, and then you have to make stronger assumptions, and you get reduced performance. And also, existing methods didn't really utilize momentum, at least not in a provable way. Uh, so that's why we actually will take our momentum optimization method and turn that into a momentum sampler. We will actually add noise to make this generalization. The question is how to add noise. Usually this is very non-trivial, but for Lie group, we have this technique of left trivialization, which allows us to actually get algorithm that is easy to design and implement, and also we can actually prove pleasant performance. So so the Lie group case, like I said before, we have some position variable G which lives in a group. This is the optimization dynamics that we previously talked about. It's complicated, but in fact, a large part of the dynamics corresponds to some conservative Hamiltonian dynamics. This guy has a very different role. It corresponds to dissipation that drains energy from the system. That's why it serves the purpose of optimization. Now, in order to make it a stochastic generalization, all you need to do is to add noise in order to match this term. This is a very innocent, simple term, but still, if you really want to understand everything, there is a heavy machinery behind it. In PDE, in optimal transport, and in particular, there's this beautiful uh, theory by fields medalist Vinali, which is called entropic hypercoercivity. I will not talk about it at all, but simply just to say, okay, so pretending you forget about the rest, and then you just look at this. This is a simple Euclidean linear dynamics. You just add noise that is additive. Okay, so you just add Euclidean noise as if everything is in a Euclidean situation, and then you get some sampling dynamics. And you can actually prove that this thing actually has invariant distribution, which is this distribution, and also under certain conditions, it also converges to this distribution. And this distribution is exactly what you want. don't worry about technicalities, but if we focus on the density, again, there's a G marginal. So the G marginal is Gibbs distribution, which is the target density. So it actually has the correct G marginal. And again, you have to turn this sampling dynamics into a practical algorithm. You do that by discretization. The technique is exactly the same as before. So we used operator splitting, and then you can get some algorithm. So details don't matter anymore. Um, you get some easy to implement optimizer that exactly preserves the group structure, and that's completely explicit as well. What I do want to emphasize is the performance guarantee of this algorithm. So we have provable performance guarantee, and this is something we are very proud of because if you think about it, if you want to prove the convergence of optimization or sampling, typically you have some notion of convexity. You can relax it. Maybe you have convexity outside the ball, or maybe you have things like isoperimetric inequality, etc. We don't really have convexity or convexity outside the ball anymore because of the geometry. Let's think about an easy case of just the easiest Lie group, SO2, which is basically a sphere. So what is a convex function? So the convex function has to live on this manifold. A convex function also has to grow as you go to the right or as you go to the left. But this manifold is actually warped around. So if you keep on going to the right, your function has to grow. If you keep on going to the left, the function has to grow. But as you keep on going to the right, you wrap around, and then the function has to grow to the right, but it also grows to the left. So you actually get a contradiction. So as a consequence, you cannot really have convex functions on any compact manifold unless it's a constant function. So you cannot hope for convexity. So we actually proved our result without convexity or growth condition or isoperimetry. All we need is compactness of the group and also smoothness of the function. So I mean, it has to be differentiable, etc. So these are really very minimal condition. I will not talk about the proof techniques, but it's a very cool mathematical thing to do. What I do want to say is this is the first underdamped Langevin algorithm on manifold. So you have a lot of Langevin algorithm for sampling on manifold, but these are overdamped Langevin algorithms. This is the first algorithm, in discrete time that is also underdamped. Okay, so this is the second part. We basically use this momentum accelerated optimization dynamics as a starting point. We add noise so that we get kinetic Langevin / underdamped Langevin type sampling dynamics on Lie group. Because our momentum is actually Euclidean, we can discretize in a nice way. And we can get a simply implementable sampler that is explicit, manifold preserving, and we actually have non-asymptotic error analysis as well. Okay, finally, with all those preparations, we can talk about generative modeling on Lie group. So the paper is online. It's not accepted yet, but hopefully, we can get some good luck with a pretty good score at iClear. So it's about generative modeling. So just in case people are less familiar with generative modeling, the task is, okay, so you are given samples, and then you want to generate more samples that are similar. And you can do that because you can assume that your training samples follow some unknown probability distribution, and then you want to generate more samples from the same distribution. So for instance, you are given animal faces, and then you can train a generative model, and then you can generate more animal faces. This is different from the sampling situation in the second part, because in the sampling situation, you have the density. Here, you don't have the density. You only have the data that are sampled from the density, and then you want to sample from this so-called latent density. This is very important problem because it sort of powers all those generative AI tools such as Stable Diffusion, DALL-E, Midjourney, Sora, ChatGPT, etc. Um, the approach that I will be talking about is called denoising diffusion model. Um, it's dominant in image and video and audio generations, but it's not method to go to at this moment for languages. So what it does is that, okay, so you take a collection of training data, you keep on adding noise, and then and then some magic will happen. So what is shown on the left is one example of a training data. So it's a datum. What is on the right is generated. What you do is you keep on adding noise to each one point in your training data set. Each one will eventually become pure noise. And then you do something radical. You say, oh, let's invert this process. So let's sample from pure noise, which you know how to do, and then you invert the process, and then structure emerges. You may say this is just ridiculous. How can you do that? The reason is because you're not really creating knowledge out of nothing. So along the forward process where you add noise, you actually add noise to an ensemble of data. So you actually characterized something called the score function. You learn something called the score function, which characterizes the evolution of the entire data density. And then you use this score function as a cheat code, a cheat sheet to actually do this inversion. Mathematically, it's actually simpler than the illustration. So you start with your data distribution D, you run some simple dynamics, for example, Eulenstein-Uhlenbeck. As time goes to infinity, everything is pushed forward to Gaussian. And then you try to invert the time of this process. You start your initial condition, for example, approximately from Gaussian. You try to invert the process. Um, Inverting the drift is easy. You just change the sign. Inverting the noise gives you trouble because you can change the sign, but then you get basically IAD Gaussian. Okay, so if you change the sign of a Gaussian, you still get a Gaussian. So you're not really denoising. So that's why you need additional help. So this red term is what you need. It's in fact you can prove if you define this as a score function, which is the gradient of log of the density of the forward process, you can prove that the solution of the second equation is basically the same as the solution of the first equation in distribution. Okay, so of course, the question is how do you get a score function? This is something that you can learn during the forward process. So this thing is actually a profound topic by itself. I will not say too much about it, but basically you use a neural network to approximate something, which in return gives you a good approximation of the score function. Okay, so that's what you do in Euclidean situation. So if your training data live in the Euclidean space, you have a very mature pipeline, which is still being developed, but it's doing amazing things already. The question is, what if your data actually live on a manifold, say a sphere or a Lie group, for example, in robotics, you deal with SO3, or in molecules, you deal with SO3 as well as SO2, etc. What do you do? If you try to mimic the success of a diffusion model, you have a lot of challenges. I should say diffusion model in Euclidean space. For example, you look at the forward dynamics. What is this? This is a drift. But if your X lives on a manifold, this thing can actually take you out of the manifold. That's not good. Moreover, what is this? This is a Brownian motion, so you actually need a Brownian motion on the manifold, but exact Brownian motion on manifold in general is unimplementable. Moreover, let's take a look at the backward process. What is this S? This S is a square function, it's a gradient. But what do you mean by gradient? So let's suppose you use Riemannian gradient. And then the gradient has to live in a tangent space, which is changing as S changes. But if you use a neural network to approximate this function, how does your neural network strictly give you something that is living in the tangent space, which changes as X moves? So then you have to do projection, etc. So you don't really satisfy the structural constraints unless you do additional approximation. So in fact, this is a problem so important that there are a lot of results. So people use a lot of approximations. For example, in RSGN, which was Best Paper Award in Europe's 22, people do projections, etc. And there is a very similar paper. Of course, there are differences, but I will not have time to talk about it. That do similar things. And then there is updated slightly different. There's a different approach called Riemannian flow matching, which is actually one of the strongest methods so far. This is best paper Ron Arp, award nominee in iClear this year. But now we have a new solution. We don't have to make any approximation because of we have this tool from part 2. So this should be part 2, I'm sorry. So what is going on? So like I said, you have a lot of places which you're not sure about. But remember, in part 2, we have this sampling dynamics, which basically allows me to push any distribution to some known distribution. So in particular, no matter what you start with, you always converge to this Gibbs distribution, which is designed by you. And moreover, this Cauchy variable is a trivialized momentum variable. So the technique of left trivialization actually gives you something which is a Euclidean variable, and your noise is also Euclidean. So to see this better, so let's just consider a simple situation. F is going to be 0, just for easier understanding. And then the dynamics looks like this. What it does is you can start with anything, and then you will converge to Gaussian in the momentum variable and uniform in the position variable. Now, if you think about a diffusion model, so you start with some data distribution, you push forward to Gaussian, and then you try to invert it. This is hard to do on manifold, but now we have some cool tools. So in fact, we can introduce an auxiliary momentum variable. You can initiate it. You can initialize it with anything, but for example, you can use Gaussian, and then you run this dynamics. Okay, you run this forward dynamics. It'll push your data distribution to uniform times Gaussian, and you can invert the process as well. All you have to do is you just add like a Euclidean score function, because this Cauchy variable is completely Euclidean. So you just use exactly what you use in the Euclidean situation. You don't have to worry about the manifold at all, and then you can go back, and then you can do generative modeling on Lie group using a diffusion approach. Okay, so that's the methodology. Let me quickly wrap up by showing some, by flashing over some applications. So like I said, you can design molecules, for example, like protein. So this is taken from this beautiful Nature paper, Nobel winning. So you can design proteins by running diffusion. So you have a data set of functioning proteins, and then you try to generate more proteins that hopefully function in the same way. And this is really just like a generative modeling on manifold situation if you just oversimplify everything. So we did simplified examples. We couldn't really do a Nobel Prize work. So we can generate protein. What you see here should really be two colors, but you can barely see them. You can barely see two colors because they overlap exactly with each other. So that corresponds to exactly match the distribution between the generated protein and the training protein. Um, we can also look at metrics. So our approach is called trivialized diffusion model. So a smaller number means better result. This is in comparison with some very strong method like Riemannian flow matching. So we actually improved the performance quite significantly. For the task of generating protein or RNA, there is a tool example just to make it a little lighter. So this is a game called Pac-Man. So Pac-Man is something interesting. So you are controlling your row. If your row goes to the left end of the board, it re-enters the board from the right end. And if you go from to the top, it re-enters from the bottom. So this game really lives on a two torus. So it lives on some manifold, and the task that we created, so this is a new problem that we generated, is to generate the maze of this Pac-Man. So what is shown in the middle is a maze generated by our method. So the maze basically corresponds to a very complicated probability distribution on the two torus. What is on the right is Riemannian flow matching. So don't get me wrong, this is already the best result that we can get from existing methods. RFM is a very strong method, but it's just, our method uses less approximation. It's specialized to Lie group so that we can be even better. Finally, let me finish up by saying, okay, so this is what I promised. So what I want to do is I want to generate quantum circuits with new functionality. So quantum circuits are actually things that that live on the unitary group. So we can actually do generative modeling on the unitary group because unitary group is a Lie group. So let me not say too much technical stuff, but just to say we get excellent result. And our approach is sort of like the only approach that is available on the market that can actually do this. Okay, so summarizing what I talked about, so we finally got to the generative modeling of data on Lie group. It's challenging because you have curved geometry, but because we introduced this left to trivialize the momentum, we actually get Euclidean-like score and also the backward dynamics, which is the dynamics that do the generation. So that's why we can do that problem with very high accuracy. That's all I wanted to say. Thank you very much for your attention and feedback.